on quantum computing with trapped ions. It's an experimental group. One of the pioneering group, I would say, in trapped ions, together with also the group of Dave Weinland in Boulder. This is the group of Rainer Blatt, or was the group of Rainer Blatt. He's still a member of the group. And I think sooner or later, probably Thomas and some other professors, they will take over.
So Rainer is still the postdoc.
So quick introduction. So yes, Thomas Monz is also head of the Alpine Quantum Technologies company to build actually trapped ion quantum computers. He is also part of the World Economic Forum Future Council in quantum computing. And he's also actually the coordinator of a big project, the European flagship project on quantum computing for trapped ions action. So he's very much involved in all the trapped ion quantum computing with trapped ions. And now it's good.
Thank you. So I was asked to give a presentation on trapped ions. On purpose, that's why you see this down that rabbit hole, like the nasty experimental details that you probably don't hear a lot about. There are some local teams. There is Raphael Rothganger working. He was a postdoc with us in Innsbruck. We have Christian Schmigelo in Argentina, whom we know. There is Alessandro Villar, who we also know, a couple of other colleagues that have been, let's say, in our ion trap sphere in Europe and now returning to South America. So you have expertise here. And my goal is mainly to show you a little bit of what's going on and maybe also correct some of these fairy tale discussions yesterday of things that don't work. And I'll just show you that we don't think it works, but we have done it already. And so just to give you a feeling of the stuff we did, so we did Shor's algorithm that was now already 6 years ago where we factored 15. And there are some neat features that you can take away from it today. For the Fourier transform, for instance, we replaced it with a semi-classical version of the Fourier transform, which reduces the number of resources by a factor of 3, because the Fourier transform is just a single qubit that you recycle, and it's not this 2n that you usually would use. And that only works because with trapped ions, we can quite easily do measurements during the computation and keep on going. We did chemistry calculations with Christine and Cornelius. We're working on 2D arrays. For instance, with Philip, then Vanya and Christian are working here on a programmable quantum sensor, where the idea was a little bit along the lines of what Kike was mentioning. It's like you have a device and you have some control knobs. And in the end, you would say, as an experimentalist, it's like these are the knobs that I have. And the theorist says, I don't care about the details that you have. Just given the control that you have, let's try to get the utmost performance out of it. And we could show that we can get really, really good clocks to work with our system outperforming all other previous clocks in terms of scaling and performance. Not these 10 to minus 21 clocks that NIST produces, but in terms of number of qubits, resilience to noise. These clocks now run fully automated using a combination of variation algorithms and a little bit of, let's say, tune-up. And this is one of these nice features where we worked with up to 26 qubits. We've also implemented topological qubits, not just the normal 3 qubit, but really 7 qubit color code. We extended that with capabilities of detecting qubit loss. We can map between different encodings. It's for those that really like error correction. And recently with Luki and Sasha, we also could demonstrate that you can build a universal gate set acting on logical qubits. So here you see really it's 7 plus 7 plus a couple of ancillas. And there we are working essentially with close to 20 qubits with error rates which are below 1%. And all of that has been demonstrated on the devices in Innsbruck. And so I'll do it the other way around. Usually you would see this list of phases and so on at the end of a presentation. So in that case, as Markus indicated, I'm doing many, many things. Sadly, many of these things are essentially politics. So the people in the lab, that's actually this entire team here, not all managed and coordinated by me. But you see here Rainer Blatt, whom some of you might know, or Christian Roos. And I'd say about a third of these people, more or less, are co-supervised by myself and Philip and Martin. And one important point, mainly for you and your audience, is we are the lab dudes. We do the nasty work with the screwdriver in the lab. We have to suffer from your ideas, so hopefully your ideas are really, really good. But at the same time, we are very much open for these ideas. If someone has a cool idea, I mean, this list should be way, way longer, but that's now something with machine learning or characterization validation or new physics, error correction of Marcos and Miguel Angel. There we have characterization and so on. Just come with these ideas, and we, like, if it's a good one, we'll happily try to implement that. In addition, I didn't want to give a presentation which is just Innsbruck stuff. I wanted to give you a little bit of a broader scope. So I on purpose reached out to my colleagues there, and so you see we got material from Jonathan Holm, David Lucas in Oxford, Norbert Linke in Maryland, he's now moving to Duke, Christian Ospelkhaus from Hanover, Tracy and Ben in Innsbruck working on networking, then Kivan is an old postdoc of ours, he's now in Tsinghua in China. Then Stick is at Sandia National Labs in the US, who gave us some data, for instance, on traps. Ulli and Ferdi are both in Mainz working on shuttling-based quantum computing, and I somehow merged all of this content into a longer sequence. So you could say, like, this introduction, and I'll skip that quickly now. Why me? So this is essentially when I started to join the group of Rainer Blatt. Back then we did teleportation. We then managed to show fault-tolerant gates. Myself, during my PhD, we pushed to entanglement of 14 qubits. This is now superseded here by 24 in some sense in my team, in my experiment. We've put this entire system inside a small rack, and we did Shor and a couple of other features together in our team. And what we did was, this is a typical lab. So you see here at the bottom, it's these individual ions. Each bright dot is one ion. And you could say for a computer scientist, he doesn't care about an ion and the laser and the color. All he sees is bright, and he calls bright 1. And sometimes it's dark. When it's dark, he calls it 0. And then the idea is, can I somehow turn that into a computer? And this is a typical lab. That's what we have at the Academy of Sciences. And what we then did was to say, but on the long run, this is something you don't want to work with. It should be small, it should be compact, it should be stable, it should be easy to manipulate. And so we turned this entire system in a single rack. So it's two little cupboards, the vacuum chamber, the lasers, everything is inside. We can control, in principle, up to 50 qubits. We have shown the entanglement with up to 24 qubits. And we did a few use cases in finance, chemistry, security, and so on. And there are a couple of gates that we can implement. So that's now this connection to Eduardo, where you say, is it a universal gate set? So we can do any single qubit operation on any of the ions, which is already something good. And now you'd say, where's my C0? Because then it's universal. So what we can do is we can do an XX operation on any two ions in the register. And this XX with local operations is the same as the C0. So here is already a universal gate set. But in addition, we can also, for us, it's just more convenient as an experimentalist. It's like, rather than having a lot of ions and I want to focus on a single one, you always start easy. So it's like, make one fat beam, illuminate the entire register, check that something starts to blink, and then you can still make it smaller. So we usually also have this collective beam where we can do collective operation on the entire register or create entanglement between all ions. And that one we can also extend, so this Möllmer-Sørensen interaction, it's not just used for collective spin flips, but we can actually also induce something like a distance-dependent coupling, which is not so much interesting for computing, but it's highly interesting for simulations. Where we can choose this distance dependence, this alpha, which essentially tells you how quickly this coupling drops off. We can even tune that. We can choose it arbitrarily between, under quotation marks, 0 and 3. Just by choosing a few laser parameters, and that's it. And that's the toolbox that we have. In addition, now finally you would say, but come on, Eduardo wants to run some code. And usually the theorists are not known for their patience. So he wants to know, like, run my idea and run it yesterday. And so it's like, okay, but how do you program the device? And so there is obviously on the control software, there's something we wrote on our own. Which is not something that you would find any documentation, and you would argue about the documentation not being good, not large enough, and so on. So what we did was there's a growing number of software development kits for quantum computing. So there's Qiskit from IBM, there's Cirq from Google, and a couple more. And we essentially support all of them, which means if you write any code in this, let's say, language, you can just send us the code and we can execute it. Partially, we can execute it directly via the cloud, but it's also just send us a little script and we execute it locally, which makes it way easier in terms of communication. Because coming back to suffering, you don't want to know how often we were struggling with like theorists in terms of your sigma y, where did you put the minus again? Did you put the minus on the top right or the bottom left? And when you talk about counting qubits, so is the first qubit the left one in your string or the right one in your string? And that can cost you days to figure out why some simulation, some calculations not doing what it should do. And so we said, let's stick to something which is standardized that hopefully makes all our lives easier. And then Eduardo said yesterday a TOEFL gate doesn't work because the performance is shit and whatever. And so here you see some recent experiments that we do. So that's essentially it's connected without going into details with error correction. And so you see here that we're working with starting at 1, so it's like 15 qubits in that case. There are a couple of C-naughts, which you can see here, and the total error rate at the end is smaller than 1%. Yeah?
TOEFL gate doesn't work on the IBM system, not
I mean, there's obviously a lot of magic going on in the background to make it work, but this is roughly what you can aim at to give you a feeling roughly what is doable. And one of the reasons, and there I agree with Eduardo, one of the reasons why it's easy for us is you can see here, essentially everything is connected with everything. And that's a pain in the neck for hardware, usually in particular if it's a solid state solution like superconducting systems, where qubit 1 can talk with qubit 2 is a question of like, is there a cable connecting the two directly? And if this cable is not in this chip, then you can't do it. You have to do some swaps and so on. That all takes lots of effort. Trapped ions, we don't have this problem. At least for system sizes of about 10, 20 qubits, everything can directly interact with everything else. And that makes the implementation of code really easy and also improves the performance. Then we had the question from Kike in terms of like, can you do feed forwarding? And here you see some quick data from Jonathan Holm at ETH. They built their own electronics with the goal to be really like, let's try to make a measurement in your computation, figure out some information, and then stabilize feedback onto the system. And in that case, how quickly you can do it, so the typical scattering, like how long does it take for the camera to sufficiently well detect, is it bright or dark, is about 100 microseconds. And the key part here, they did a lot of electronics work. They can extract the information now in about 100 microseconds. Usually that's only order of about 3 milliseconds, but if you write the code on your own and you know it's like dedicated for your goals, this is about as fast as your typical gates. So like 100 to 200 microseconds is the time scale of an entangling gate operation. Yeah?
Yeah, I would like to ask about the cloud access.
Yeah?
Is there an API or is it completely discretionary with any of the scripts?
Well, as you wish it. We usually, it's like if you look at IBM Qiskit, there is a backend for us on AQD, which you can use, but then you can also just write this, like you add at the top your token, and we can run it locally, depending on what you have in mind. And one cool feature now is also, is like for error correction, if you want to make these changes, how long does it take to compute what you want to do? And that's on the timescale of nanoseconds. And so they use this successfully now, and we heard about GHZ states before. So it's like you can have 3 qubits, and what you want to do is you measure your XX stabilizer. That's what we heard from you before, just an hour ago. And your ZZ stabilizer. You check, are you in the right state, and then you do feed forward. If it's a parity is inverse, then you just fix it, make it the same way. You do that for X and Z, and here you can see that they did 20 rounds of feedback on that system. And the other thing which I personally find really cool about that is you see it's flat. And that's exactly what you want. I mean, if you think about it, usually you would assume, well, if I measure something, I feedback, you heard about there's coherence time and lifetime and all of that. Yeah, but every time you make a measurement, you stop the clock. You did the projective measurement. You got the info, which state are you in, you do this fix, and then this clock starts counting from scratch again. You really say it's not like a T1 time where you say with a certain probability it decayed, because you took a measurement, you really know, did the decay happen, yes or no? And depending on whether the decay happened, you make a correction. And that's why this actually is flat, and you can keep that one going on in principle infinitely to keep the system at the state where you want it to be. In some sense, you can also think about it like a Zeno effect. It's like you just measure. If you find an error, correct it, and then you keep on going. And that's more or less also the idea behind error correction. Because you always figure out a measurement, you reset your clock, and then you go on. And that just gives you a rough idea of what we can do with ions. And then there was also the statement that we can't do 2D stuff with ions. So here again, you see these non-existing 2D stuff, 2D arrays of ions. So Leni and Dominic are working here on a specific strap design, which you can see on the left-hand side. And here they can conveniently work typically with 95 to 105. That seems to be one of the sweet spots. They can work with about 100 ions in the context of simulations to work on 2D arrays. And the last part is now...
How do you track those ions? With optical axis?
No, that's just an RF trap. It's the same trap as any other RF trap. It's just the tricky part is, as you can see here, it's actually a sandwich. It's not 2 blades, but it's 3 blades. But that's all. And then you adjust the RF in such a way that the potential is not like a cigar-shaped one, but more like a pancake-shaped potential. And then you can get a nice 2D array of ions. And this is exactly where Christian now wants to do this distance-dependent coupling in 2D together with single ion control, so that you can now push for interesting simulations. And the last part, and like we can go into all of that in more detail as we move on in the lecture, you could say, there will be a limit at some point. It's like these laptops. It's like it's not that when we think about HPC, like high performance computing, you get a larger and larger CPU. At some point, what you do is actually you have one CPU, a second CPU, a third CPU, and you start to hook them up. Can you do the same thing with ions? And so there is an idea on paper. It's like you can couple an ion to an optical cavity, which makes sure that it collects the light, and you can send the light over. And for instance, in the UK, that's like now data from David Lucas. The idea was the project was called 2020, to have 20 traps with 20 ions each. So you would have up to 400 ions with optical interfaces. And so they are still pushing in that direction. But one thing which I find really cool here, you can see this essentially network speed between the two nodes, where it's on one hand side, it's the fidelity, like how good does this connection work. On the other axis, you see how fast it is. 4 different platforms, so ions, NV, neutral, quantum dots, and so on. And here, this is now ion trap data, again, showing you that in terms of fidelity, it's by far the best in fidelity, but also in speed, it's actually really, really fast. So if you think about it, that's now on the order of about 1 kilohertz. So that's more or less a factor of 10 slower than our entangling gate operations. And what David Lucas is working on now, they have 2 vacuum chambers with 5 ions each and this optical interface. And they control it now as if it would be 10 in one complete system. And the end user, so like if you send some code, you don't even have to care whether is it 5 or 10 or whatever it is. This interface, as like the protocols in the background, take care of all of that. And so again, that gives you a rough idea of what we can do with ions. Here are some highlights on purpose, a summary. T2 time from Kivan has been achieved with up to 1 hour. Whereas if you think about other systems, it's like microseconds, milliseconds. They have a coherence time of 1 hour on admittedly 1 ion. Gate fidelities are on the region of 10 to minus 3 roughly. That's been achieved in Hanover, NIST, Innsbruck, a couple of others. We can work with 20 ions. Again, Maryland, Innsbruck, and a few are working in that direction. Honeywell has really outstanding data for this quantum volume, which is one of these measurements for connectivity, gate fidelity, and so on. We have 2D architectures, we have interfaces, and these interfaces are typically slow, but at least for ions, we can make them almost as fast as our gate operation. And one thing that's coming also now more and more is, you previously saw we were filling up this entire lab, and you want to make it smaller. There are now new processor designs where the light is using integrated waveguides. So you don't have to have a big lens or anything anymore. It's the light is coming out of the chip. Rather, if you want to control laser light, usually we use an acousto-optic modulator. It's like a little piece of crystal with a transducer on the side, speaker. It's the size of half a wallet, let's put it roughly that way. These are now fully integrated already into the traps. There's nothing you need to do and control from the outside anymore. And NIST was also pushing to make sure that the detection works within the chip. So rather than having a large camera somewhere on the outside to see the ions, that's also included in this system. And ideally, if we make it properly, you could say there's nothing stopping us from having the entire quantum processor in a vacuum chamber the size of a wallet, because there is no window, there is no acoustics. It's all a cable which you need to connect, and then you can go on. Just in terms of what's going on in our field. And yes, this might sound expensive and demanding and so on, but I think there's one cool thing. Ion-trap quantum computing doesn't have to be expensive. It's like you can, if you are willing to do it, you can do it, if, let's say, cost efficiently. And here I want to just give you a feeling of what we did 20 years ago. The very first traps we had in Innsbruck, it was a piece of wire which we just bent around and soldered, and that was for some of you, the old barium experiment. That was just handmade. There was nothing special with the machine shop and gold coating and so on. It was a piece of wire, you make a little loop, and that's all you had to do to get the first trap going. How do you get the ions? Like nowadays you can buy sources and so on. Back in those days, it was like a little metal tube. We put the calcium inside with like just a wire, pushed it in. It was good enough. It worked. It was a little bit more dirty than you would have it nowadays, but it works. It's like if you want to make it cost efficient, you can make it cost efficient. We bought laser diodes and we just built our own diode lasers. We didn't buy them back in the days because we didn't have the money. It got to the point, and that's why you see the dumpster here. Marcus knows that, like the old lenses that we have, for instance, in some of the experiments which are still installed, they have some awkward scratches on the surface. And the reason was that one of our old assistants, who is now a professor in Mainz, he went to the dumpster of Swarovski. So Swarovski has his headquarters, let's say, in the vicinity of our university. He drove there by car. He took the thrown away lenses out of the dumpster, brought them to the lab, and we just glued them on metal posts to somehow use them in the lab just to keep the costs as low as possible. And it's good enough. It's not great, but if you want to see a bright dot, it's good enough. The first AOMs back in those days, we couldn't buy them. Again, we had no money. But someone noticed laser printers. If you buy a laser printer which switches on and off the light, it's actually using AOMs. And so we talked and we got a full box of old broken laser printers, and we tore out the AOMs from the broken laser printers to use them in the lab. Nowadays you get a nice little box and you can get a special coating for the wavelength and so on. It's like, come on, you take what you get. We tore them out of the printer, we just used it, you checked, like you made some labels, like these ones are better for red, these ones are better for blue. But it's like, I'd say 50% of the stuff was either home built or broken components where someone else didn't see any value. But for us, it was good enough to get going. And with that background, I think it gives you a perspective that experimentalists can be inventive. It's like we know how to suffer. And yes, you can make amazing good experiments work with very, very little. And once you have it, you can push on top. And I think a final point along those lines is, at least for me, it feels that the ion-trap community is very, very friendly. It's like a co-competitor, not necessarily a competitor. So we had, for instance, some stuff in our lab which we didn't need anymore. And then we know from Christian Schmigelo in Argentina, it's like, okay, there are some components, could you make use of it? Rather than throwing it away, we put it in a big box and we shipped it to Christian, where he said, like, you can adapt it for your own needs, but you got a vacuum chamber and a cavity and a vacuum pump and some electronics controllers. Everything we could, let's say, give away without the university complaining too much. We put into a box and then it disappeared.
We can send 2+U as well.
Yeah, no, so like Raffi we already have on the radar. So it's like we recheck what kind of inventory we have where the stickers are so old that no one notices anymore.
The quantum computation.
Yeah. And with that, I'm actually coming to the outline of this lecture. We'll start today with how to trap ions, and then we could say, let's say you have a stronger background on algorithms and AMO physics. We can talk about initialization, measurement, manipulation of qubits. We can talk about errors and decoherence, characterization, verification, validation, error correction and fault tolerance, scaling up, down, and scaling out, where here I'm talking about how do we make the processor smaller. Here, here's smaller. Scaling up is like how do we store more and more qubits for better and better control, and how do we hook up these different processors. So this is now more or less 10 groups. We have 8 hours, and I'll just make it 10 hours anyway. But what we can and should do is likely, we'll talk about ion traps today, and then we just choose as we move along. If you say it's not so important to know how a photomultiplier works or CCD camera advantages, disadvantages, let's skip that. But yeah, it would be nice to be reminded about Doppler cooling, sideband cooling, pumping. Let's redo this one, and then we jump directly to manipulation. There's a little bit of leeway where your interests are, and we just pick and choose according to your interests. So first one, how to trap ions. And because the focus was on quantum computing, there's this old 100 million times repeated De Vincenzi criteria, where it's like, if you want to build a quantum computer, ideally you have very well characterized qubits. And one thing about very well characterized qubits is, for me, with ions, it's like I can have a calcium ion. It's going to be the same calcium ion in Riken in Japan. It's the same one that Raphael will have in South America, and it's the same in North America. We know the properties. It's reproducible because it's the same by nature, and that helps a lot there. We need to initialize that. AMO physics, 50 years. We really know how to do that very, very well. Coherence times from Kivan, and you have the slides on that. We can push that from, like, our team in Innsbruck, we have now seconds coherence time. You can push it to minutes and hours if you go into different encodings. All of that motivated just from AMO physics. The universal gate set is straightforward. The measurement is also easy. We can do these connections. It's even telecom compatible, which I find really, really interesting. And we can do that even at larger distances. You can redo this list now from a more experimentalist point of view. Yeah?
I'm really sorry. My questions are very, very, very basic.
Yeah? Perfect. That's what experimentalists like.
Because I've been theoretical physicist, but not on these things. When you speak about a trapped ion.
Yeah?
Okay, I'll repeat. That I'm very sorry because I've been working for 20 years in theoretical physics, but not on these things. So for me, everything is new, although I've been hearing about it. Okay, so my basic question is, when you speak about a trapped ion,
yeah,
is that 1 qubit?
Well, that's what I meant. A trapped ion so far, and we'll go through that with initializations on. If you think about your, I assume it's physics 3, whatever you learn in the 3rd semester, atomic physics, it's like an atom usually has many, many levels. Okay. And we have to have sufficient amount of control that when we then start to manipulate this ion, we ever only work with 2 levels. And if it's only this approximation, I think that's an important part, it's an approximation of this multi-level system as a 2-level system, then we call it a qubit.
Okay, okay, and then you try to put more
ions in there and control them step by step.
Okay. Okay.
But that's also for us the hard and also interesting aspect. It's like the qubit honestly doesn't exist. That's a mathematical concept that Eduardo might like, but for me in the lab, I have to deal with about 8, 9, 10 levels, and I need to know about polarization. Like, we need to be better at AMO physics than computing, actually.
Okay. So that system of trapped ions is supposed to be a quantum computer?
Yeah.
Okay. Good.
Are there more questions? Good. So we have to have two-level systems, and we need to approximate them accordingly. We need to be able to individually control the ions. They should be stable. We want to demonstrate entangling operations and how to do that, and we need to measure them. And again, that's more like from an experimental point of view. What kind of capabilities do you have to have on these devices? And yeah, if you would look at current literature, I mean, that's an old picture actually. You can build quantum computers with ions. You can build them with photons, with superconducting systems. All of these systems you can approximate as a two-level system and then think about how to implement quantum computing. So for us, trapped ions, we have control up to 50 ions. We can use them as a computer. We can use them as a sensor. We can use them as a simulator. Same actually happens with superconducting systems. You have, again, 50 qubits simulating and computing, not so much for metrology and sensing. And this 50 qubit number, it's like Google has about 50, IBM has now 400, D-Wave claims to have, I don't know, 2,000, 4,000, something like that. 7,000. Or 7,000. The question is always like, how much of that can you actually control? And so that's why quantum volume and other metrics come in, because you could say, I can really easily generate 1 million qubits if I want to. All I have to do is switch on the light, because I get millions of photons from a light source. It's just that the control is a little bit limited of these photons. And so just having a large number of qubits doesn't tell you anything about controllability. And this is why some of the older metrics very simply says, like, yeah, marketing, I have more qubits doesn't mean anything, because your control might be bad, or your reproducibility might be bad, the stability could suffer, and so on. Single photons could be way better, because like a photon, besides absorption, it doesn't decay, polarization is relatively stable. Philip Walter and others are working on that. Can Weiban obviously is working a lot with photons. Simulating computing, and there are this subgroup of sampling problems. Rydberg, now Rydberg with neutral atoms from Marcus. So Rydberg is really, really cool for neutral atoms, because you can have really, really fast gates. It's Quera, Lukin, Antoine Brouvet, Pascal, and so on. They all work with 100 to 200 qubits now. But one tricky part for you to remember is, like, if you know from AMO physics, Rydberg blockade, that usually only works in this vicinity of the atom where you do it, which means you only have short-range interactions. They are really, really fast, but they tend to be short-range. And so that then has an effect of what you can do and how good the performance are. And there is one good thing now. There are people that say, these Rydberg gates, they are really super, super fast. Can we map those onto the trapped ion, let's say, toolbox? And Marcos and Ferdinand Schmidt-Karl and Mainz and others are working in that direction to say, okay, we can achieve coherence times on the order of seconds, minutes, even hours. But like one figure of merit that you can think of is, well, how many operations can you do? If Eduardo, and we had the questions before in terms of depth, how many gates can I do? You could say, well, the simplest one I can think of is take my coherence time, divide it by the gate time, and then I have a rough number for how many gates I can do. It doesn't include fidelities and so on, but it's like just by coherence time divided by gate time, this is what I can do. Okay, so we can push and make the coherence time better and better and better, but you can also push in the other direction and say, can I make these gates shorter? And so now with trapped ions we have minutes, seconds, minutes, even potentially hours coherence time. But with the Rydberg interactions from Marcos, you can say I can make these gates a factor of 10 to 100 faster. And now you could say, wait, 100 nanosecond gate at the clearance time of seconds and minutes, there is really, really lots of room to get some interesting algorithm going. That was the question? Okay. Cold atoms, there's like optical lattices as well, with different kinds of control, and then, for instance, NV centers are sometimes pursued as well to do quantum computing. For me, the biggest challenge with NV centers is the reproducibility. It's really nice. You could have a chip in your wallet and you can bring it along, and it's like robust and it works in principle room temperature and cryo. But the very moment you say, I'm really happy with this chip, make a second one, the second one very likely has completely different properties. And as the chip sizes increase, characterization becomes a pain in the neck. So reproducibility of the chip, of your processor, is really one of the biggest problems. And from what I heard, it's like, I think the D-Wave machine, if you make it warm and cold and you want to recharacterize it, it takes like on the order of weeks to get everything recalibrated. Yeah?
Could you please instruct us on the difference between these neutral atoms and cold atoms?
So cold atoms, so there are, most of the interactions are based on Rydberg, but there are some ideas, for instance, to do collision-induced gates. There is simulation work with dipole-dipole interactions, as Francesca is, for instance, working on, so in the context of more of simulations, but then they always are interested to understand, can they map ideas from simulating towards computing? And so this is more...
Rydberg is more computing,
digital. I would say it's more on the computing side, but like Antoine Brevet and Michel Lukin are working in that direction, more focused on computing. And here you see a typical string in Innsbruck, where it's about 100 ions, and in the center you can see about 50, which we then can easily control just with individual laser pulses. So, again, nasty, nasty stuff, because that's what the experimentalists have to deal with. So again, remind me, which lecture is it where you have atom physics? Which semester is that? Third? Second? Third?
Depends where you are.
So, 3, 4?
For me, it was more to the bit of the course, but I imagine that other universities maybe in the half.
Yeah, about 4th semester. Let's put it that way. So late? Now come on, you have to start earlier with quantum.
Reality is different here.
Yeah. So for us, it's usually in the 3rd semester. And you start with the simplest one, which is hydrogen. And everyone who did hydrogen with Zeeman and hyperfine splitting and whatnot is like, that's good enough, and then you never ever want to usually deal with 2 outer electrons. It's like, you do it if you have to, but ideally not. And so hydrogen is cool. We know it quite well. It's easy to control. We know roughly the level scheme and what shifts there are and so on. We can calculate that a lot. And so that brings you to the question, now you have this periodic table, how should Raphael choose which ion? So what would you do? You can choose any of these elements. Like, which one would you choose? To be a good, let's say, easy to control system.
Something not that heavy and something not that lighter. So that
Well, but the weight doesn't really matter. The electric fields are so strong.
Not the weight, but in the sense that it would be sensible enough to any form of energy could make the ion go away.
One step back. That's experimental physics. We don't answer with a concept. Just tell me which one you would choose, and then explain why. Here? No. Well, the first column is neutral. So if you would try to ionize it, you would actually end up with a hydrogen, like a what's it called, noble gas configuration, and that's the worst thing you could pick. Exactly. So you start with the second column. Yeah? No, It's really, you pick the second column because you have two outer electrons, and now it's neutral. What you do now is you remove one electron to make it charged, but you just have one outer electron, which makes it look essentially like hydrogen.
Why do you need it to be charged?
Because I need something to keep it, and I use electric fields to store the ions. It's just the easiest thing you can think of. Is like just use some electric field to somehow charge it. In terms of strength, Coulomb direction is one of the strongest one we have. And so you want to have something on the sec. And now Raphael has the next problem. Like, which one do you choose? Because again, experimental details, nasty stuff. There are numbers and there are units. And that means there are transitions, and you have to think about not just which transitions there exist, but can I actually build lasers for that? Can I have all the lasers that I need? So here you see barium. Barium was the first species we had in Innsbruck for one simple reason. Not because it was heavy or light or anything. The reason was the two main lasers that you need is this essentially 493 laser and the 650. Both of those I could get from a normal diode. Everything else, when you look at beryllium, 300 nanometers, deep UV, there was like no way 20 years ago to get 300 nanometer light easily. Pick something really simple as possible. And so barium was very, very convenient. And later on, then calcium, actually for the details, is like the 866 is easy, and the 400 nanometer can be realized back in those days. For instance, taking a titanium sapphire laser and frequency doubling it. Why barium sucks, or it's like it becomes interesting now, is actually this other transition that we need. We need this D state, and that means we need a laser at 1700 nanometers.
I'm sorry.
Yeah?
Some minutes ago, you told me that. Thank you. I was asking that some minutes ago, you told me that it was desirable to have some years ago. Sorry. Some minutes ago, you told me that you desired to have some system when I asked about the ion trapped ion, that it should behave as a two-level system.
Yeah.
But here you have more than two-level system.
Yeah, that's what I meant. This is what we as experimentalists have to deal with. As a theorist,
This is the real life.
Yeah, that's real life. And as a theorist, you would actually here only pick one state, and out of this D5 manifold, you would only pick one state. This is what you would see. It's like you can think of me as this gatekeeper of unusual information. It's like there are two levels, that's all you need to deal with. The other levels and the lasers and all of that, this is something that you don't have to deal with.
Okay, so you're going to explain how do
Yeah.
we deal.
But that's what we have to start with. That's the painful thing. It's like because it determines how you actually set up your experiment. It's like you need to choose which ion. And when you want to choose which ion, you look at these level schemes and you have to figure out which lasers can I get? What do they cost? Are they even available? So the 1700 nanometer laser, there are currently two solutions more or less which work at least somewhat, but there is, for instance, NKD, which wants to do a test program with us because they don't know how reliable the laser works. And they said, we would give it to you at a really good price, but it might not work. Or might not work as stable as it should be. And so that's why we ended up in Innsbruck initially with calcium, because there all the lasers are, let's say, more or less conveniently available. Still painful overhead, but it works. And now we come to how do we make a two-level system out of it. And now we start to cross out stuff. And just for the moment, focus on the left-hand side. You could say, well, I get rid of states that I don't care about. So there's a ground state, there is an excited state, and this excited state has a lifetime of about 1 second. And 1 second is really, really good, because if you think about AMO physics, like typical lifetimes are nanoseconds and so on. So this is a long lifetime for all interactions that we have in mind. And so we call this one the ground state, that's called 1. The excited state is 0. And then there is a helper state which I can use to figure out in which state is my ion. Like I can switch on a laser light, I excite it to this state. If my electron is in ground state, I excite it, it decays. So there's some echo. It decays, and as it decays, I can get on a camera a bright dot. Whereas if the electron is in the excited state, I would switch on the laser, but the electron is kind of stuck. No photons would get scattered, and the photomultiplier or the camera would just say it's all dark. And that would be the simple version, but you can also use it in a slightly different configuration where you think about the ground state. You can say, the ground state is split. You could have, for instance, hyperfine splitting. There are ways where you can, for instance, say, I make a Raman transition to couple these two levels, or I couple them directly with microwaves. But bottom line is all of them look the same. It's like you have a two-level system and another transition which we can use to detect whether the ions are bright or dark. And this method of just scattering light on a different transition is called electron shelving. What we can do is on the ground, on this system, it's like the lifetime is essentially infinite. We can have really, really good clock transitions in terms of like they are also insensitive to magnetic field. If we think about MF equals 0, MF equals 0 transition, it's like if there are magnetic field fluctuations, nothing changes because your prefactor in your magnetic field shift is 0. And here it's essentially the T2 time in these systems has been achieved with on the order of about 1 hour. Now, again, how do you make atoms or ions? Before you can make an ion, you would first wonder how do you make atoms? Because it's like, okay, there's this lump of calcium or a lump of barium or it's like this piece of metal, and I want to somehow get that somewhere in my vacuum chamber. How do I do that? And it's like the simplest solution is take a little tube, fill it up, fill it with calcium metal, fill it with barium metal, send a current through. So what you can see here is just connectors. You send a current through, there's a high resistance, it becomes hot. A little bit of the metal, as awkward as it sounds, starts to evaporate. And then you have this cloud of atoms which just move somewhere to the front in your vacuum chamber. And if these things are carefully designed, in terms of diameter and length, you can actually get a nice collimated beam of atoms coming out of it. These ovens are really like, this is the simplest thing, you can build them on your own. The ovens are obviously full. I mean, in terms of like, there's lots of metal inside. You can run them for decades. So the experiment I'm still working on has been under vacuum now for about 20 years. And it's still the same oven. I mean, because it's not just running out. But there are also a couple of little bits and pieces that can go wrong. If you think about it, we had chosen atoms out of the second column. Everything which is on the left-hand side of your periodic table, and the farther it is to the left-hand side or to the right-hand side, tends to be chemically very reactive, which means it likes to oxidize a lot. If something oxidizes, usually these oxide layers are really hard and thermally stable, and they don't like to break. Which means if you have an oxide layer at the top of this oven, because you assembled it, you had it on air, didn't do it quickly enough, this oxide layer could mean that you can't get ions out or atoms out. And so one way of fixing that is like you fill it under atmosphere, for instance, argon gas. You fill it and then you seal it with indium. Indium has a very, very low gas pressure and the melting point, which is essentially barely above room temperature. So indium is really nice, and then you have it sealed. You can use it when you make it hot. The indium goes away, there is no oxidation and so on. One drawback is, well, yeah, you fill this oven. You can have air trapped inside. The other thing is when you send current through, well, these oxide layers, they can get very hot. This oven can explode and so on. So there's like, while it's really simple, there is a certain risk associated with these traps. So usually if you make a design of such a vacuum chamber, you try to get at least 2 ovens in, because one might not do what it should do. What we do these days, which worked amazingly well, is just ablation loading. So you take your target, barium, calcium, whatever you want, and you just send short laser pulses on the surface. It's like, again, it's like heat, but the neat part is with ablation loading, if there's an oxide layer or not, you just burst through it. It's like a short pulsed laser, costs 5K or so. You send these laser pulses on the surface and you can essentially evaporize anything. That also works for some of the more tricky materials where, for instance, the melting point and so on would be higher. And, you can't have virtual leaks because you didn't fill any tube. you don't have anything which gets hot inside the vacuum chamber, which means if you have a dense assembly, you don't run into any heat problems where suddenly something thermally expands and therefore moves. It's just a little target, you send your laser on it, and you get your ions out for the center of your trap. And so now we have the atoms roughly where we want them to be, whether that's now from an oven or an ablation target. So how do we make ions? Again, if you want to be really, really simple and cheap, you can start with an electron gun. 2 electrodes, blast a lot of voltage on it, you get an electron gun out. This works, but honestly, you don't want to use it. The problem is that these electrons go everywhere. Any dielectric surfaces, they just charge up or discharge, but in vacuum, nothing ever really moves away. So you have uncontrolled charging of surfaces and so on. So it works, but you tend to ionize whatever is around because your electrons just hit also background gas and you can have molecules which you then might trap in the vacuum chamber and so on. And with the ions, you have another problem. So if the electrons hit at high energy the atom, it might be that you don't single ionize, but you can double ionize or something like that. So you have something in the trap which is charged, but it's not what you want to have. And because it's now double ionized, the optic transition and nothing works. So all the cooling, initialization, manipulation doesn't work. So ideally, you want to have something where you can really make sure you only ionize once, and it's really specific to it only ionizes, say, calcium and nothing else. And you can do that with just photoionization. So what you do is you take a 2-photon transition. What you do is first you excite the ion to one specific level, and because it's atoms and the transitions are very well known, you get, let's say, you excite calcium, but this laser won't excite any other species. It won't excite barium, it won't excite molecules and so on. And then with the second laser, you can ionize it, you like give it in total enough energy that the electron is gone. The cool thing is now your level scheme and everything changes again. So this ionization only works once. And the next cool thing is it's like you only do it at the location of the lasers. So you know that it's nowhere else it's generating ions. It's only generating ions at the location where those 2 beams overlap, and it only does for a single species. And so this combination of ablation loading with photoionization gives you really, really high quality to make ions. One problem is like, okay, now we come to this question, how do you trap atoms? So like, so far we only did like how to make an ion. So far I didn't even talk about how do you trap it. So you could say, think about back in AMO physics, you can use magnetic dipoles, you can electric dipoles, or you can use electric charge. And depending on what you have in mind, it works for different things. It works for neutral atoms, it works for cold atoms, or here atomics and ions, so atomic ions and molecular ions. And with the electric field, this is something we want to work with. And so the idea is, short summary, is like you have an ion with a certain mass, and the poor man's version is think about just a normal 1D potential. It's like a salad bowl. You put the ball inside, and if it's inside, then yeah, it shouldn't fall out. What we care about is, okay, what's the curvature? That's in some sense what we call the trap frequency. It determines all the dynamics of like if it moves away to the side by a few nanometers, how quickly do we repel it? And the other thing you might care about is the depth of your salad ball. So it's like how much energy does it take for me to hop out of my potential to lose the ion? And for us, now there comes again something that you don't like at all, because now we do an exercise, but not like Eduardo does it. So we have room temperature thermodynamics. What's room temperature in energy in electron volt? It's a number everyone should always know. About 20 to 40, depending on whether you do the 3.5 or not. So it's something 30, 40, 20 milli-electron volt. A typical potential there that we can achieve in our traps is on the order of 1 eV. And now we can nicely see, wait, if you have like energy from the environment on the order of 30 milli-eV versus 1 eV, I have like e to the minus 100 in your Boltzmann to say what's the probability that I lose an ion when there is a collision with background gas. So this gives you an idea why working with ions is so convenient, because we can load ions on Monday and we keep them more or less the entire week. because it's just so rare to lose an ion. That's completely different, for instance, when you compare it with neutral atoms, when a dipole trap has on the order of 50 to 100 millievolts. So it's like only a factor of 2 or 3 larger than what your room temperature energy is. And so it means if there is a collision, there is a relatively high chance that you lose ions. And so for us, that reflects now onto why it's so convenient to work with electric fields, because they are so stiff, they hold them, and they hold them very, very deep in the potential, so we don't lose the ions. This one is nice on paper, and you can write down your equations of motions and the size of your wave package and the frequencies. There's just one thing. It's like, okay, we need it in 3D and not in 2D. And if you try to do it in 3D and you go through a Poisson equation, you figure out, with DC potentials, there is no way I can ever trap an ion. Because if you think about it, there's always some dip somewhere where my ion, in some sense, can roll out. But what we can do is, we can, for instance, use a bending trap. We can use a magnetic field to make the ion circulate, or a Paul trap, where you, rather than using a static potential, you use an RF potential. And this is essentially the thing that most of us are using. You just have a couple, like you have a dip voltage, which is static, and you have a ring around it, which is where you apply RF, and you are done. Then you have a confining 3D potential where you can load and store the ions in the center. So again, physics stays more or less the same. You have charges, you have the forces, and then you have to solve these equations of motion. What you then see is this trap frequency. There is this motion of the ion, where I said the stiffness of the potential determines the dynamics. But then there is also an extra term which is coming from this trap drive, because you apply RF, you would say, well, I have to see the RF frequency. Ideally very small, but there is something there which is called micromotion, and it's there always in your trap dynamics, but to a very large degree we can ignore it. So this is the secular motion which we care about, which determines our interactions. The micromotion is just something for you to keep in mind, that this is something in the background which can, let's say, limit the performance of your system. Yeah?
You told us that this is operating for how long time?
So we have that vacuum chamber, some of them are 20, 25 years old. So the oldest chamber that we are using is from 1997, I think.
Since then, one trapped ion has been...
No. It's the vacuum chamber is the same. And the oven is the same, and the trap is the same. Like nothing was changed. The ion at times can drop out, because as we said, it's like your trap depth is 1 evolt. You can sometimes, or when laser cooling doesn't work, or what sometimes happens, you have a power shortage and all the RF and all the DCs were gone, then you might lose an ion. But to give you a feeling, with barium, we once had the same ion for 2 weeks without any laser cooling. Because a single ion is easy to store, and it's so heavy that even smaller collisions don't do anything.
Thomas, hello?
Yeah.
Can you back 2 slides, please? Once more. Here, is it possible to vary the potential V0 like an optical LED,
sure,
and yet control like an optical LED?
So here, this one is a number that we change a lot in terms of, because it determines how far the ions are apart. It's like this, how much do you push the ions together, and this is this radial confinement. So the V0 we can change, and this omega we can change. This omega usually is on the order of 30 to 50 megahertz, depending on what you have in mind, and this V0 usually is like a 5 to 10 watts amplifier, and then you use a resonator to further enhance the voltage.
Okay, thank you.
So was it that you wanted to have a local potential?
Local potential.
Well, this is based on it, like we can talk about it. I have in this scaling up, I have some slides. We can also do something which looks like an egg carton, wie sagt man denn, this egg storage shape with lots of little potentials where you make rings and you put rings next to each other, and that's how you can build 2D arrays. That also works. So yeah, you can see here the large motion, you can see the micro motion, and the simple designs really can be something simple as, like in that case, it would be the parabolic shape of a ring plus the tip voltages, and you get then a confining potential along those lines. But usually this one is a pain in the neck because you have no real optical access. Because if you think about it, like where would I send in lasers? So you drill some little holes into these shapes and you hope that like everything is nice and aligned. But in terms of figuring out if something goes wrong, it's a pain in the neck. So what we actually opted for is rather going for a ring and having this ring with 2 tip voltages. So this is a schematic again, and here I see the actual vacuum chamber that we used from about 25 years ago, where all of these elements really were made by hand. So again, if you want and if you're curious to build an ion trap on your own, it's not too hard if you don't set your expectations too high. But yeah, this was all home built with, yeah, as you can see, a couple of wires and that's it. Yeah. Then we'll skip a lot of that. So there are, for the exports, you need to carefully choose voltages and trap drive and so on, because there are stability, like the micro motion, it's a driven motion, and actually the underlying physics is similar to mass filters. And if you think about mass filters, which you might have heard in some of your lectures, mass filter works in such a way that you on purpose have a charge and mass ratio and electric fields chosen in such a way that only one mass essentially passes through and everything else gets thrown away. And the same thing applies here. It's like you need to carefully choose what voltages, what trap drive and so on to make sure that you can stably trap your ions. But yeah, I'll just skip those details. Bottom line is, you get now a confining potential, which looks like that. But if it's rotating, you get an effective potential. And now we change the geometry a little bit. Rather than having a ring with 2 tips, we now make it 4 rods. And now my potential doesn't become a spherical confining potential, but it becomes something which looks more like cigar-shaped. And if it's more cigar-shaped along these axes, now I can load many, many ions, and you can think, now I get 1, 2, 3, 4, and now I have my bit string. Because if they are bright and dark, I have my zeros and ones. And so here you see the confining potential. You can turn that mass filter into many, many, let's say, design considerations. This is one of the older designs that we have in Innsbruck. This is one of our workhorses. You can also do that in segmented traps. You can also do it in let's say, just pieces of glass, which you then gold coat. There are so many ways you can design your own traps. But typically, it's like the cool thing is also you can't do much wrong. It's like if you don't really screw up, you will always find something where you can load a couple of ions with a simple structure. Again, we skip the stability diagram. One thing is about the stability now, the voltages determine what you get. So you can have this nice linear string, which we mentioned. So we have some bright dots, but I can also lower this radial confinement. You can think about it, all these balls. If I really squeeze them together, it's a nice linear string. If I now lower this radial confinement, because they all repel each other, because they're all charged, and it's like they all want to get away from each other, now suddenly I get something which looks a little bit elongated, and you can make them almost ball-shaped, and then you can go into a regime where it's really, like say, spherical or a pancake and so on. And that's some of the ideas where in the very beginning, where I was showing you that we can have these pancakes of ions, which are like a 2D array with a trivalent connectivity in your register. Yep?
Sorry about not ignorance. For you, it's preferable. Thank you.
So what?
Okay. Sorry about not ignorance. For you, it's preferable to have these trapped ions in which format? In a pancake?
I personally prefer them in a linear string for the moment. Because if there is a pancake, there is why I mentioned the micromotion before. There is one axis where there is no field. So if you think about it, we had these 4 blades in the tip. So the symmetry axis is along the trap. If I have the ions in this axis, then they wouldn't see any of the micromotion. And any kind of motion is always bad. So for me, at the moment, I prefer to have them in a linear string, because then I have high level of control. But just to disclose it here at that level as well, if you do it properly, and Christian thought a lot about it, you can have ions which are in this pancake shape, where yes, you have micromotion, but if you now choose your beam configuration properly, even this motion essentially doesn't play a big role. But it took more, let's say, 10 years for people to really look into all these possibilities on how to make the pancakes and which gates to work under which configuration and so on.
Thanks.
So that was an ERC at Monz, I think, just to figure out how to do it and consider to implement it.
But can you address with the laser individually?
Sure. We have this, when it comes to manipulating, we have like a full block on how do you address single ions.
Any case.
Yeah. So here are some numbers, typical plate distance, a millimeter, yeah?
But you have to address them with lasers.
Yeah.
But then they're fluctuating.
No. So when you think about the trap parameters, the size of the wave package is on the order of about 10 nanometers. So it's like really static, and the cross-section is just coming from the wavelength of the light. So the cross-section is on the order of about a micron, depending on which ion species you have. And so all of that is static and easy and straightforward. And 6 millimeters, 1 millimeter, you see here that if you have just a reasonable mechanical workshop, or you on your own in your student workshop, you can start to assemble a trap like that. There's actually nothing which is super challenging and so on. So again, you can make them on your own if you want to. Inside a vacuum chamber, it would look now that way. So here you see these radial plates and the tip voltages on the left and on the right. And what we changed now is previously these tip voltages were always closed. Now we make a little hole in these tips so that we can just send the beam right through the axis, which makes it easy to illuminate all the ions, let's say, in the same way. Yeah, and a couple of details now just a glimpse of how much you can go down the rabbit hole, and that was a little bit of the start of the lecture. It's like you notice, why is it golden? So like previously we used stainless steel. You want to make sure that it's non-magnetic, because magnetic fields and so on can be a pain in the neck for Siemens shifts and so on. Okay, so stainless steel, as good as it gets. We got one, we had a special block of submarine steel, which is made non-magnetic. And then you use thermal annealing and so on. But then at the end we said, like, come on, that's just a headache. Let's change to titanium. Titanium is like immediately easier in terms of having nice non-magnetic properties. But as all metals rust. So you have oxide layers, and these oxide layers can be a problem. So you use a titanium plate, but you gold coat it, because gold doesn't have an oxide. And so you can make sure that your surfaces are all nice conducting and there's nothing in between you don't want to have. And then I mentioned before, wait, I said 10 watts of RF power inside a vacuum chamber. Well, vacuum is really, really good at insulating. What happens with those 10 watts? It's like, okay, it's a resonator, you have little loss, but the thing gets warm. And so in order to make sure that it doesn't get too warm, what you see here, this, it looks a little bit like grayish stuff. That's actually artificial sapphire, because sapphire is a really, really, really good conductor. And so we just use this artificial sapphire to make sure that the heat and everything goes away as fast as possible. And that is another reason, because when you make your trap, like when you switch it on, the thermal expansion of all your components would mean your system moves a little bit left, right, up, down. And if I mentioned before, the ion distance is on the order of micron. I mean, thermal expansion efficient is on the order of 10 to minus 6 typically. So if the temperature changes by 10 or 100 degrees, it's really easy to move a couple of micron up and down. For a typical system, you don't care. But if your beam is aligned with the ion at the spot size of 1 micron and suddenly the thing moves 100 micron up and down, then you have a problem. And so that's why you can play then some additional games of sapphire and titanium and so on, and copper to do proper thermal anchoring. That's where you can then talk with Raphael and others on how to do that. Trap depth, here just the numbers. Trap frequency in megahertz, which means that dynamics is really fast. We can drive fast gates. The depth is electron volt, so we can keep ions for a long time. Optical access, usually you want to have as much as possible optical access for the camera, for addressing and so on. The thermal anchoring is fairly easy. Fabrication and alignment, because everything is so large, it's also straightforward. There's nothing really challenging in any normal workshop. Materials, you have to a little bit careful because you put it inside vacuum, so it needs to be something which doesn't outgas, so don't use plastic. If you want to have something insulating, maybe Kapton or so, that still survives. But the other thing is, because it's inside the vacuum chamber, and as you will learn, vacuum chambers usually get baked, which means you operate them for some time at 200 degrees C. It should be something which doesn't start to smoke or burn or something like that. Yeah, and here you just see some different trap designs. It doesn't have to be a bulky one. Here you see some of the traps where we also can make 3D traps, but with distance sizes on the order of just a few hundred micron. And there's one development which I really like. It's called selective laser etching. So you take a piece of glass, and you can use a laser beam to just burn essentially a little bit into the glass, which weakens its structure. If you then put it into an acid, you can etch out whatever you burned, like say a signature, into the glass. You can, with acid, you get rid of it. And now you can suddenly go to structure sizes which are on the order of 10, 50, 100 micron on top of glass. You fabricate whatever structure you want to have. You do a gold coating, so you go to your friendly solid state guys and do a gold coating in one of their vacuum chambers, and that's it. And then you also have small segmented traps, which you can rather easily build on your own. System design considerations, yeah, okay. If we want to build this system, I said, okay, you need lots of RF power, you need a resonator, and you want to have good vacuum. So we'll talk a little bit about different pumps, and you want to have good optical access, which means the windows, like your glasses, if your glasses would be non-flat or let's say significantly more surface rough, then you would have a distorted picture. If you have a distorted picture, you also can't have a good spot size. It took us now, I think, 4 or 5 years to find a really good company for good viewports.
Yes. Can you just explain one more time this one? Because like this one is, well, completely different, right? This is like some kind of chip or what?
If you think about it, so here you have 4 blades and a tip. What I do now is these 4 blades are on purpose on an angle of, let's say, 90 degrees relative to each other. Now imagine I just flatten them out. What you end up with now is what you see at the bottom.
Okay.
It's the same thing, just a little bit tilted, and then I have everything in one surface. And now I can also make traps using lithographic methods.
I see. But like, I don't understand. What are these lines here coming from the left? Like.
So, yeah, well, you have to somehow hook up all the electronics, the RF power, the DC, and so on. So
okay. I was thinking that maybe this was related to.
No.
Okay, fine. I understand. I see.
So, before Marcus gets angry with time, so there's plenty of details that we have to deal with, which is like, how do you get the RF in? How do we get the pump done? What about the lasers and the optics access? Here you see a vacuum chamber. That's our workhorse quantum computer, which we had for 10 years. The white box is just a mu metal shield to shield magnetic field fluctuations. On the inside, there is a vacuum chamber, but here you see a huge pump. There is the RF on the top, the ion pump on the side. Here, left and right, we can do the detection with photomultiplier and CCD cameras. And there is a couple of lasers and electronics. That's the nasty stuff that we have to build so that you get the 2-level system. and most of the time, the theorists don't know what kind of pain it is to build it. And then, yeah. But yeah, when you look through the window, here you see again this bladed trap. It's just now a little bit on an angle, where here would be the tip. There is the other tip. The lasers come from the left and the right. And we can illuminate and do all the magic on these lasers. Here we still have an old oven, simply because 20 years ago we didn't have anything else. Nowadays we do it with ablation loading. And I just skip lots of these stuff now in terms of like, just keep in mind we have these ions, we have a typical distance on a couple of micron. And again, the important part is the lasers that we had were all on the order of 300-400 up to about 1 micron in nanometers, like 400 nanometers, 1 micron. And if you want to focus down a beam, more or less you cannot focus it more down than what the wavelength is. So if you have a 1 micron laser, it's about 1 micron spot size. But if the distance between the ions is 4 micron, I can send an individual beam on an individual ion. And that's why I have this individual control. It's just the parameters, all the numbers match up, that we can do individual addressing of ions in these registers. And here you see some of the pictures that we had, and also a little bit of a timeline. So we started with 1996 with 1 or 2 ions. We could go to about 10. Then we did 30, and now it's 70, 80, 90, 100, depending on what we want to have. Equidistance behavior and modes, there is motion. Obviously, if we think about it, we described everything as a harmonic oscillator. And what you would think of in a harmonic oscillator, well, you can have this one. And so here you see exactly what the ions would do if you excite them. But if you think about the ions, they can also do this one. And that's what we call breathing mode, because it's like your chest breathing. You can also have that one, for instance. And all these modes are nice because they give us control, but at the same time, they also mean that all talk a little bit to each other, so we have to control them very, very well. Yeah, and here you see just a picture of how this breathing mode can look like in real life. And now I'll skip all the stuff about vacuum and how to clean it and how to make a pump and what an ion pump is and what the neck is, like these non-evaporative getter materials, which really help a lot these days to get better vacuum. Titanium sublimation, which was used before a lot. Nowadays, I know very few people that still use them. Partially because also in our, like not in our group, in Tracy's group, one student once accidentally hooked up such a pump the wrong way and managed to break the vacuum because essentially one of the valves essentially tore up because it was so hot. That then the air got in, and then he started the plasma, which destroyed part of the experiment. And it was like Northern German, and it was amazing to see. It's like Konstantin. He was like, "That's going to cost you 1.5 years of your PhD, like hooking up 2-3 cables the wrong way around." And the only thing he did was like, "I'll call it a day, and tomorrow we'll fix it." Gives you a perspective on how high our, let's say, pain threshold is in a lab. Yeah, details on how to bake and that you can use a cryostat. You might notice that for quick trap development, people rather want to go for cryostats because you can get a good vacuum notably faster than just always losing 2 weeks on baking. Has some advantages and disadvantages. But yeah, after 1 year, ideally you are at this point where you have your trap made and inside a vacuum with ovens, with everything, and then you can start to load ions. And that would be the first run. So it's like we now, ideally you at least remember the second column is the magic column for which ions to pick. You learned a little bit how do we turn a lump of metal into an atom cloud and subsequently into an ion cloud that we can store. And we have heard a little bit on ions and vacuum and so on. And that's it for today.
Okay, I guess there's not so much time for questions, but maybe we can have 1 or 2 questions still.
Once again, very, very basic level question.
Yeah.
Could you go back slides to where you have some images before the whole breathing?
Yeah.
Before that.
Yeah.
Once again, please. When you have some orange background and some before this, more, please, once again. No, we're not arriving yet. That one. The previous one. Yeah. On the right-hand side. Are those the trapped ions that you see?
No. Huh? That's just dirt.
Oi?
It's just dirt.
It's just a?
Dirt.
Dirt. Ah.
So because depending on how good you make the gold coating, it's like if you do it fast or slow, it determines the granular size of the gold particle on the surface. And so when you then make a high resolution picture, it's essentially you can see the surface roughness. And ideally, so you can do sputtering, or you can do electroplating. And usually it's like if you make a thin coating, you get a nice surface structure. But if you then just dump it in and do quick electroplating, then you can get wiggly surfaces, depending on what you do.
Okay. And another question, when you have the system interacting, breathing, and so on, so your qubits are not independent. I mean, they're interacting one with each other.
That's the magic. That's what you need. Because if you want to have entanglement, if you want to be able to say, my first qubit needs to talk with the second qubit, you have to have some kind of interaction. And this Coulomb interaction, this joint moving, that's actually how you can build interaction between the ions.
Okay, but when these people speak about the gates and so on, where do you place the gates?
So we talk about that in the second or third session, depending on what the students want to hear. So what you do is, let's say the Pullman's version from the idea from Sirac and Zoller from 1995 is, think about two ions. What I can do is I can shoot a laser on one ion in such a way that the string starts to shake. And now I can send another laser beam on the next ion in such a way that it says, if you're shaking, make a bit flip. If you're not shaking, do nothing. And that's how you can, like this one controls the joint motion, and then this other part essentially says, depending on the joint motion, do something. And that's how this very, very old idea came up on how to build a quantum computer with ions.
Okay. Thank you very much.
I'm still around, so if you have more dirty questions about vacuum and lasers.
Exactly. So I think we should actually go for lunch. So thanks everyone.
Mein Körper sagt eindeutig, es ist irgendwie schon später Nachmittag.